Hi, this is my process project screencast. I'm pretty sure it's supposed to be 6 minutes. So step one was to do our um, dynamic material and energy balances. So we started with the total mole balances, with the total mass balances on the two tanks. We assumed constant density, constant volumes, and no reactions, and then we were able to solve for our flow rates inward and our flow rates out. And then for our energy balances, we assumed adiabatic, constant volumes, constant UAs, or like no UA for tank one because there's no coolant, uniform mixing, and then constant rhos and Cs. And from there, we were able to derive our DT1 DT and then our DT2 DT. This is just all from our practice quiz. It's just algebra in there. And then step two was doing our transfer functions. So I grouped all these stuff from our energy balances. I grouped them all by constants. Then I Laplace transformed them, and then from there was able to solve for these two transfer functions. And then I was able to solve for all the constants that I grouped above as well. Here's my summary table. From there, I was able to plug those into a block diagram down here, as you can see. So like these are the two transfer functions, and then these are the plots. Um, just like by looking at the diagram. And then to simplify this and like get rid of that inner loop here, I did an algebraic version of the loop law. I just plugged in T2 into this, and then solved for T1, and then I was able to get T1 over TS as well as T1 over Tn. Yes. And just a bunch of algebra there, putting it in standard form. From there, once it was in standard form here, I had another like bunch of constants to bunch together here. I put this into a new modified block diagram that's simpler and it doesn't have that loop anymore. And then I was able to put that into like our whole system. So here's like our whole system originally. And then here is it without this inner loop here, with my new transfer functions. So this is our modified closed loop diagram. Here's step five where I fit my own data to get KB and tau v. I'm actually going to pull up the Excel really quick. Here we go. So here is the data that I was provided for here. And then here's like the green are my, this is like my fit. And then you can kind of see the orange behind it is like data I was provided. So I did two approaches. The first one I did was the easy approach where K is just the change in your output over, like, yes, the change in your input. So my output was my final steam temperature over my initial steam temperature. My change in my input was like how much we changed the controller setting at like t equals 0. And then 63.2% of the ultimate change is going to be like 1 tau v. So it's just like 1 minus e to the negative 1, I think. So I figured out k was going to be the delta output over the delta input, and then I was able to do like 0.632 times km plus my t bar, my steady state one, to get the temp at tau v. Then I had to interpolate to get tau v because it wasn't like at an exact time. You can look at that if you want. But this is my final tau v. And then the hard approach was the data fitting, which this is my fitted equation. And then I plug that in here, and then I did the difference between my fit and the experimental data. I summed that all and I squared it, and then I minimized this while changing kV and tau v. And yeah, that's about it. I'm gonna go back to, let's see, let's go back to project. Okay, perfect. Yeah, I pretty much talked about this. And now we derived T1 of T. We know that T1 prime over C prime is going to be third order because the steam temperature, like the valve, is first order, and then the T1 prime over TS is second order, which we know from above. We can do like a Heaviside equation for this, and then we need to multiply a bunch of stuff out to get all of our alpha 1, 2, and 3. So I first multiplied everything by this and then set S to this and plugged that in, and I got alpha 1. And then we just tried setting S to 0 and S to 1, and that worked and gave us alpha 3 and alpha 2, all in terms of like alpha 1, and like they were all in terms of each other. Also, we know that zeta is greater than 1 because it comes from two real positive taus, tau 1 and tau 2, so the system is overdamped. Then I Laplace transformed here. It's a step change, so C is going to be M over S. Multiplied that out. This part of the equation was just number 13. This one was number 23. There's like a bunch of algebra you can look through if you want. This gave me my final equation, adding in T1 bar, and then here are all of my constants from above that I collected. And then finally, going back to the energy balances, I set these equal to 0 because it wanted the steady state values. And then I used nominal temperature values, plugged in T2 of tank 1 into the T2 of tank 2 to solve for UA without T2 as the intermediate in there. So that's all my algebra there. And then QR min is when UA is just greater than 0. So I set this equal to just greater than 0, did a bunch of algebra in here, and then I got that QR min is going to be this value. So our QR has to be greater than or equal to that. Okay, thank you.